Okay, in this video, we want to find the inverse Laplace transform of a function by using a table. So just like in that previous example where we used a table of Laplace transforms, there's something called the inverse Laplace transform, right? And it involves basically going from the S domain back to the T domain. So remember when we did the Laplace transform of a function, we took it from the T domain to the S domain. And in this case, we're doing the reverse operation, and that's why it's called the inverse Laplace transform. So the first step basically is, I always find it helpful to pull out the constants here. So we do, instead of working with Laplace inverse of 5 over s cubed, we can pull the 5 out. And so we're just going to be 5 times Laplace, inverse Laplace of 1 over s cubed. And basically, step 2 is selecting the right theorem. Actually, we have, this is theorem 4.2.1. We're going to select the right equation from this theorem. This is basically the table of inverse Laplace transforms, and it's on page 218 in the textbook. And the way we use this is recalling when we use basically the form that matches the form of our problem. And what I mean by that is that notice how you'll look in the table and you'll see a bunch of different forms of inverse Laplace transforms. And the one that catches my attention is this form here, n factorial over s raised to the n plus 1. And that's the reason being is that in our function we have, remember this is going to be a constant. N factorial will always be a constant. And we have s raised to the n plus 1. So if n is a constant, then comparing it to our problem, we have 1 over s cubed. So we can actually conclude that n is going to be 2, because in our problem we're going to have s raised to the third. So if we conclude that n is equal to 2, notice that that necessarily generates a 2 factorial term in the numerator. So that's assuming that if we say that n is equal to 2, then that means that our function would normally be, like 2 factorial over s raised to the 2 plus 1, right? And that makes sense. But we don't have a 2 in our function. We have just 1 over s cubed. If we had a 2 over s cubed, that'd be perfectly fine, right? So what we have to do in order to fix this, small deviation from the equation is we have to actually divide by the 2 factorial term to fix this. So because we don't have that in our function, right? We're generating it, so we have to get rid of it somehow to match our function. So that's what's done in step 3. Remember, the 5 has already been factored out, so the 5 is, we're not working with the 5. It's just being multiplied by whatever the Laplace of inverse Laplace of 1 over s cubed is. So we're going to end up with 5 times 1 over 2, right? We're getting rid of that 2 factorial by dividing by 2 factorial, and 2 factorial is equal to 2. So we get 5 times 1 over 2 times t squared, and that turns into 5 over 2t squared. And the process is, whenever you solve inverse Laplace transforms, it's a little bit weird because the Laplace transforms, you're typically used to going from, if you're transforming, something, you're going usually from one, here to here, and typically you understand it best in the, the forward direction, so the Laplace transform. But the inverse Laplace transform is just basically the going backwards. So we can always check our work if we say that, okay, I know that finding the Laplace transform for me is much easier than finding the inverse Laplace, but you know that you've tried to find the inverse Laplace, you say 5 over 2t squared. We can actually check that work here. And this is an optional step, but we can, it's pretty useful to see. The question is, does the Laplace transform of 5 over 2t squared equal 5 over s cubed? And this has to be true if we've done this correctly, if we've taken the correct inverse Laplace transform, because that's exactly what we're doing, right? If we take the inverse Laplace transform of 5 over s cubed, that has to give us 5 over 2 t squared times t squared. Otherwise, it's not the right solution. So we can use the regular Laplace transform, Theorem 4.1.1 table, and we'll find, first of all, we can factor the 5 over 2 in the front of the Laplace transform. So we'll save that for the outside here. And then we'll take the Laplace transform of t squared. And that's going to be 2 factorial over s raised to the 2 plus 1, which turns out to be 2 over s cubed. And the 5 over 2 times 2 turns into 5. And so the calculation is correct. So you can see how going from the inverse Laplace and the Laplace and backwards, you can always check your work. If you're more comfortable performing one operation, you can always say, if you arrive at an answer and you take basically the inverse of the answer, you should get your original problem. All right.